Hello, I'm Richard Hammack. Welcome to my Calculus 1 course. Today, on this first lecture, I'll give you an overview of the entire course. The first thing you should know is that calculus is built on the foundation of algebra and trigonometry. It's not like you studied algebra and trig and now you're moving on to a new topic. Instead, in calculus, you'll use algebra and trigonometry extensively, daily. The other thing that you'll need to know at the onset is that calculus is phrased in the language of functions. You know that a function is a mathematical construction that models how one quantity depends upon another. For our purposes in this course, it's important to realize that functions can be put into two groups. On one hand, there are the linear functions that have the form f of x equals mx plus b, and they have very simple graphs. Their graphs are lines. That's why they're called linear functions. The slope is m, the y-intercept is b. On the other hand, there's everything else, what we call the nonlinear functions, and their graphs are not straight lines. You know well that linear functions have lots of nice properties. They have simple algebraic expressions, y equals mx plus b. They're easy to graph. It's easy to find the x and y intercepts. They have this nice notion of a slope, rise over run. And also y changes at a constant rate with respect to x. So as x increases, y increases at a steady, unchanging rate. But for nonlinear functions, every nice property of a linear function is paired with a not so nice property. They have potentially complex expressions. They're hard to graph. Intercepts can be hard to find, depending on the function. There's no immediate notion of slope, and y changes at a varying rate with respect to x. So we're confronted with the dilemma. Linear functions are simple, but as you know, most useful functions in science are nonlinear functions. Now, given that, I'm going to tell you the simple idea that underlies all of calculus, and it's amazing how simple this idea is. It relates the complex nonlinear functions to simple linear functions. And to illustrate it, take a nonlinear function like this one graphed here, y equals f of x, and let's single out a point P on the graph of that function. And imagine that you have a very powerful magnifying glass, and you're going to look at that point P up close. And when you do so, the magnification is very powerful, so this curve really hasn't had a chance to bend very much in that field of vision. If you see a little bend, take a more powerful magnifying glass and look at it. Up close, this nonlinear function looks like a straight line. It looks like a linear function that you could extend. Now, imagine you get a straight edge and you extend that red line as indicated. Now you take away the magnifying glass and you look at your point P, and up close, this y equals f of x curved nonlinear function is indistinguishable from this red linear function if you just look near P. And we call this function, this linear function, in red, this straight line, the tangent to y equals f of x at P. So here is the central idea of calculus, and it sounds so simple, but it really is the central idea. Up close, nonlinear functions look linear. It's hard to believe that calculus can be built on such a simple idea. But that's exactly the case. Let's move on to talk about some of the key concepts of calculus that stem from this very simple idea. I've drawn a graph of a nonlinear function f of x, and let's take a particular value of x, like right here, and look at the tangent line above x. Of course, there's nothing special about this particular value of x. I could choose a different x and get a different tangent line. So notice that for these values of x, the tangent line above x has negative slope, but as x increases, that slope is getting closer and closer to 0. So the slope of the tangent line depends on the value of x. Because the slope m of a tangent line depends on the value of x, that slope m is actually a function of x. It changes with x. And what shall we call that function? Well, we're already using f to be the function under discussion that we've graphed here, the nonlinear function. Let's call this related function f prime. So the slope of the tangent line at the point x is f prime of x. So here, for this particular value of x, f prime is a negative number, but it's getting closer to 0. And now for this value of x, f prime of x would actually be equal to 0. It's the slope of this tangent line, which is now 0. Increase x, the slope becomes positive and gets bigger and bigger. So f prime of x, which gives the slope of the tangent line, m, grows. So we have a picture here where at a point x f of x on the graph of the nonlinear function, we have a tangent line whose slope m is given by another function, f prime of x. Now, this other function, f prime of x, will turn out to be a key concept in calculus. It's actually called the derivative of the original function f. Here's the definition. The derivative of a function f is another function, f prime, for which f prime of x is the slope of the tangent line to y equals f of x at the point x f of x, just as illustrated here. In this course, we'll spend a lot of time defining derivatives very carefully and coming up with rules for how to compute them. For this particular function f of x that we graphed, if we look at its derivative, f prime of x, it's a function, so it too has a graph, and it gave the slope of the tangent line. Over here, for these values of x, the slopes were negative, and then at x equals 0, the slope was 0, and then the slope turned positive. So you'd expect the derivative, f prime of x, to have a graph that looks something like this. It goes from negative to positive as x increases. Another way of looking at the derivative is to say that it's the rate of change of f of x with respect to x at a particular value of x. So here's the picture. Here's an x. We have the tangent line. Its slope m is f prime of x, but that's also rise over run. So if you think about this little triangle right here, small enough so you can't tell the difference between the tangent line and the graph of the function. Think of the run as a small change in x, and then the rise is the corresponding change in y. So rise over run is how much y changed divided by how much x changed. That's the rate of change of y with respect to x. That's the slope m, which is f prime of x. So f prime of x is the rate of change of f of x with respect to x. We will encounter some key processes in calculus, and the first and most important one is this. differentiation. Given f, find f prime of x. And as I said, we'll come up with lots of different rules that tell you how to find f prime as an algebraic expression if you know the algebraic expression for f. Now the other process is the opposite of that. Given f prime, the rate of change of f, find f. And we'll come up with lots of rules to do that. That's called integration. So the processes of differentiation and integration are opposites of one another. And we'll spend a lot of time in this course talking about them. And the course will culminate with the result that ties these two processes together. And it's called the fundamental theorem of calculus. At this early stage, we don't even have the language to state the fundamental theorem of calculus, but I can explain it in a somewhat incomplete and imperfect way using area. What the fundamental theorem of calculus says is this. The area under the graph of f prime of x between x equals 0 and x equals a is f of a minus f of 0 square units. And this probably needs a picture. Here I've graphed f prime of x, y equals f prime of x. That's the graph of the derivative of some function f. And between x equals 0 and x equals a, and under the graph of f prime of x, there's this shaded area, this gray area. And the fundamental theorem of calculus says that that area is f of a minus f of 0 square units. To get the area under the derivative, you plug in a to the function, and you subtract off what you get when you plug in 0 to the function. It's the difference in the function value between a and 0. Now, we'll express this a little more carefully when we get to it in this course, towards the end of the course. But for now, just to give you an overview, here's what it is, as we can express it now. Now, let me describe a thought experiment that indicates why you might believe this result, this fundamental theorem of calculus. And I'll modify this graph slightly. In this thought experiment, I want you to imagine that you are engaged in some business enterprise where you're earning money, and every day, beginning with day 1, and then day 2, and day 3, all the way up to day A, you record your earnings in a bar chart as indicated here. So on day 1, you earned $275. On day 2, you earned $300. On day 3, you earned $275. So you record your earnings in a bar chart. And let's say that at the end of each day, you deposit your earnings in the bank without spending anything and never withdrawing any money. Then this bar chart indicates the dollars per day that go into your bank account. On the first day, $275, then $300, and so on. Now, let's say that f of x is your bank balance on day x. So these dollars per day, that's the rate of change of your bank account. How many dollars per day are added into it each day? It's the rate of change of your bank account. So if f of x is the quantity, giving the amount in your bank account, then dollars per day is the rate of change of that quantity, which we have up here being the derivative f prime. So y is equal to f prime of x. So roughly stated here, we have a graph of f prime of x, And notice that the shaded bars are the area under that graph. And if you look at each bar, its area is the amount of money you made on that day. The base is 1, and the height is the number of dollars you made. So 1 times the number of dollars is the number of dollars you made. So the total area of all of these bars, the shaded region, would be the total amount of money that went into your bank account between day 0 and day A. And what would that be? It's f of A, the amount of money you had on day A, minus f of 0, which is the amount of money that you started with. So f of A minus f of 0 is the change in your bank account between days 0 and A. And you'll notice here in this thought experiment, the area under the graph of f prime of x is f of A minus f of 0, just as is stated here in the fundamental theorem of calculus. So it's not too much of a stretch to say that, or to expect that in general, under the graph of any continuous function, f prime of x, the area between 0 and A is f of A minus f of 0. That's an illustration of the fundamental theorem of calculus. So on this slide, really, I have given you the entire content in an overview, the entire content of the course. Of course, there are many, many details that we'll have to work out. But on this slide is pretty much everything that we're going to talk about in this course. And of course, there are applications. We'll see lots of applications. One application of calculus is this. It's optimization. Given a function f of x, find its maximum and minimum values. And the maximum value here would occur at some number a, where notice the slope is equal to 0. And also the minimum value occurs where the slope is equal to 0. So that perhaps gives you some indication for how the derivative of a function can tell you the high and low points of the function. And there are tons of places and applications where you'll want to maximize or minimize some quantity, optimize it. And calculus provides a means of doing so. Not surprisingly, another application of calculus is to find areas and volumes of complex regions. Also, to solve problems involving motion and rates of change. Motion and velocity is actually the rate of change of position with respect to time, and calculus deals with rates of change. And carried to its natural conclusion, or natural application, you can actually use calculus and the concepts we discuss in this course to describe planetary motion, the way a planet revolves in an ellipse around the sun. And here's the planet, and there's the sun, and this elliptical orbit is indicated here. And there's a red tangent line here, which would be how the planet would move if suddenly gravity was switched off. It would fly off like that. Now, we're not going to develop planetary motion in this course, but we're going to get to the brink of it in what we discuss with integration and differentiation. We'll almost be at the point where we could solve a complex problem like this. And in fact, calculus was first invented way back in the 1660s by Isaac Newton, precisely to describe planetary motion. So there are countless applications in all branches of science and engineering. I've just given 3 applications on this page, but calculus is a major tool used in all branches of science. And this course is an introduction to it. With this, let me outline the course. Because calculus depends on, or is built on the notion of a function, the first part of the course is going to be a function review. And you already should know a lot of this material, but it's been my experience that most of my calculus students don't know it well enough, so we're going to spend a lot of time reviewing functions. Then in part 2 of the course, we're going to get to the first idea that separates algebra from calculus, and that's the limit. We're going to use a new concept called limits to get to the slope of tangent lines, and that's going to lead into the process of differentiation, finding the derivative of a function. And in part 4, we'll look at applications of differentiation. And finally, in part 5, we'll talk about integration and the fundamental theorem of calculus. And that will bring us to the end of the course. So most immediately, coming up next is part 1, function review. There are a number of lectures here. The next lecture will be function fundamentals. And you probably should know all the stuff already in function fundamentals, but look at it anyway to refresh your memory. We're going to spend some time reviewing trig functions, inverse functions. We'll have a lecture on exponential functions, another on logarithmic functions, and then we'll talk about inverse trig functions. And once we've done that, we'll be ready to move on to part 2 of the course. So coming up next, function fundamentals, and I'll see you there. Goodbye.